but we're going to try and implement, or I'm at least going to try and give you some tools to help you get to a point where you do feel comfortable enough approaching these diagrams. Now, one of these tools, I don't know where to put this. I haven't left myself any space, and this is really my own fault, is using Dr. CPT. Now, I'm pretty sure we've spoken about Dr. CPT before, but if not, we're about to speak about him. And Dr. CPT is basically a little, English people, anagram that we use, or that I use, to help me remember that there are certain important characteristics given to me in diagrams that are going to be helpful. Now, another thing I want you to remember, and I've said this to you guys before, is the fact that particularly in geometry, okay, so anything where there's a diagram, analytical geometry, functions, Euclidean geometry, cubic graphs, all of that sort of stuff, what we're putting on the diagram is there for a reason. So if, for example, I'm telling you that you have a pair of parallel lines, that is there for a reason. At some point in your answers, you should be using that fact. So these are just a few little characteristics that are going to be useful for us and that we need to remember. So D stands for diameter. Okay, this is useful because particularly in a circle, if we are told where the diameter of a circle is, A, we know that we potentially have some radii that we can work with. Okay, we potentially have some radii we can work with. I'm just trying to draw a straight line unsuccessfully. But we also know that when we know where the diameter is, we know that we have an angle subtended of 90 degrees. So we have angles in a semicircle. So diameter is very useful, A, for radii purposes, but also for angle purposes in terms of the angle in the semicircle. R stands for radii. Radii, very important to know for one of our more basic geometric reasons, in that we know, I don't know what that is, we know that all radii are equal in length. So if you have a triangle drawn, you know that the angles opposite those equal sides are the same. My diagrams are really poor. I do acknowledge that. I'm sorry. I can fix them if you want them fixed, but hopefully we get the gist of what I'm saying. Okay, C stands for cyclic quad. That's not how you spell cyclic. Not how you spell cyclic either. Cyclic. Okay, cyclic quad is useful to us for many reasons, but mostly because we've got 3 different cyclic quad reasons. So the first being terrible cyclic quad, that our opposite angles are supplementary, so they add up to 180. The second being that your exterior angle is equal to the opposite interior angle. And obviously, if we had angles in same seg, that's a cyclic quad reason. Okay, so there's a whole bunch of reasons that stem from a cyclic quad being a cyclic quad. A cyclic quad, just in case we've forgotten, is one where all 4 vertices of the quadrilateral sit on the circumference. It has to be on the circumference. You can't have one vertex on, say, for example, the center. All of them must be on the circumference of the circle. P, parallel lines. I don't know what's happening today with my handwriting, but anywho. And this is where fun or fuzz comes into play, corresponding co-interior alternate. We can either prove that lines are parallel, or we can use the fact that we have parallel lines to prove angles are the same. And then the last one here, T, is for tangent. You have got 3 tangent theorems that we use. Theorem number 1 is your tan chord theorem. Do my best to draw this as well as humanly possible. She said with confidence and then failed. So your tan chord theorem. You also have your tan perp rad theorem. So if you have a radius drawn, you know it's perpendicular to your tangent at that common point. And you also have tangents from a common point. So if I had another tangent here, we would have equal lengths. All right, so there's a fair amount that we can gain just by identifying these 5 things from our diagram. Right, this wasn't the neatest thing in the world. This is all on the like information pack in Euclidean geometry. So this Dr. CPT is there, but it's just one tool that you can potentially use to try and make sense of your diagram. Okay, obviously you will find things that work for you, and as we go through, I'll try and give you some little suggestions that might be helpful. But you, at the end of the day, you're the one writing the paper. You need to figure out what makes sense and how you do it makes sense for you. Okay, I'm just going to wait there in case you want to screenshot that masterpiece on the side there. Otherwise, we'll have a look at our first question. Right, now generally the way these Euclidean geometry questions are structured is you will get a proof question, just accept it now. So that's why I was saying earlier, you're either learning your proofs and you're banking those 5 or 6 marks, or you're not and you're losing 5 or 6 marks. I think it's pretty silly to lose 5 or 6 marks, particularly now that I've given you hints for your theorem proofs, but your choice. You then have questions that are very much a grade 10, grade 11 circle geometry level question. Tell me the size of this angle. There's no algebra involved yet, nothing like that. Still very basic. We then increase into like an algebraic example. And then often the more complex question involves the similarity and proportion that we need to then work with. Okay, so hopefully we're going to get to look at all of those tonight, but if not, we do still have Wednesday on the section. All right, so this is from 2 years ago's trial paper. We have in the diagram PRQT is a cyclic quadrilateral in the circle with QR equals QT. Chord RT is produced to S, and radii OP and OT are drawn. PRT is equal to 42 degrees, and QTS is equal to 146. Now, this is where Dr. CPT comes in. Identify these things if you have them. You can use a highlighter to highlight them. You might want to color coordinate. So you might want to say, okay, cool, everything I'm highlighting in one color is stuff that's given to me. Everything I fill in another color is stuff that I work out. You do whatever you want to do, okay? I prefer multiple colors, but I do also understand that that might be overwhelming for some people. I just like the multiple colors because I can then see distinct characteristics of my circle. But again, whatever works for you. So we are told that we have a cyclic quadrilateral. So we are told that PRQT is a cyclic quadrilateral. I don't know why I've got an arrow all of a sudden, but whatever. And PRQT, so sorry. And if we go and actually sort of identify that quadrilateral for ourselves, we can see it's a cyclic quad because all 4 of its vertices sit on the circumference of my circle. And that's what I said a cyclic quad was earlier. So here's my cyclic quad. That's great. It means all of my cyclic quad theorems can be applied in the situation. We were then also told that QR is equal to QT. That again has been given to me by those little tick marks on those sides. And we are told that we have the radii OP and OT. Okay, OP and OT. So immediately I know those 2 side lengths are equal to each other because they're radii. I'm then also given certain angles. This is on my diagram, so I'm not going to stress about it. PRT is equal to 42 degrees, and QTS is equal to this 146. Okay, so it just allows me to identify what I have. I don't have any parallel lines, don't have a diameter, I don't have any tangents, but I do have a cyclic quad, I do have radii, and this will hopefully help me as I go into answering these questions. So the first question asks me to determine, giving reasons, the sizes of. And the first one is angle POT. So POT is this angle up here. Now, guys, particularly in this first question that we're given, the mark allocation is generally 1 mark for a statement, 1 mark for a reason. But as we move into our Euclidean geometry, those marks are often combined. So you get 1 mark for both your statement and reason. So if you've left one off, it means that you lose that mark. So always just remember to be giving your reasons. It says in every question, giving reasons or with reasons or whatever. So you're always reminded of it, but just don't make a silly mistake and forget that. All right. Now, this is only 2 marks, which tells me that I can go immediately to my answer with my reason. They are my 2 marks. Now, excuse me. we can see that because we know that OT and OP are radii, we know that this point O is our center. The second I know where my center is, I also need to be thinking of my center theorem, i.e. angle at center equals 2 times angle at circumference. Now, there are lots of variations of this theorem. One is sort of the straightforward, sort of like arrowhead looking image that we kind of expect it to be. The other form of this is when you work with the reflex angle at your center. And the form that we're looking at here in this particular diagram is the one where you have your angle at the center, but then your angle to circumference almost looks like an angles and same seg situation, but it's not, because you've got one angle at the center and one angle at the circumference. And that's what we have here. So if we follow from this chord PT, we follow to the center. And if we follow from the same chord PT or the same arc PT, we see our angle at the circumference at angle PRT. It would be much easier if you could see my fingers going, but basically you follow to the center, and then from the same starting point, you follow to the circumference. And so what this is telling me is that we have an angle at the circumference of 42 and an angle at the center, which must be double that. And so POT is equal to 84 degrees because of angle at center equals 2 times angle at circumference. Okay, so just remember these 3 forms of that theorem. We can test them to you in any of these sort of, my words today are just, we can give it to you in any of these formats. Okay, in this one, we were given one that kind of looks like an angles and same seg, but please remember that because one of the angles is at the center and the other one on the circumference, it is not the case. Okay, so now that we know this piece of information, what I like to do is I like to fill in information as I go. You obviously don't have to. You can do whatever you want. I would do it in a different color, just so that I'm not confused by what I've been given and what I have. But I now know that this angle is 84 degrees, which obviously we can't read because choices were made in life. So let's do this. 84. I don't know if that's better, but at least we know it's 84 degrees. Right, the next angle is asking me for R1. Okay, so R1 is this angle up here. So I'm going to give you guys a second. I want you to think about it, and if anyone has any suggestions, you can raise your hand or you can put in the chat. Let's see if we can figure out what R1 is. Okay, Loretta, I do see your hand. I'm just going to give everyone a chance. Unless it's a question, just let me know.
Ma'am, I also have like a quick question that I wanted to ask. So, ma'am, do you mind redrawing how you did when you figured out the angle O? Like,
Okay.
I don't know if you understand what I'm trying to ask.
Yeah, no, I do. Okay, so what I'm going to do is I'm just going to make my pen a little bit thicker and we'll do it like this. So essentially what I'm saying to you is your angle at center and angle from circumference sort of originate from the same arc, or you can use the same chord. So we've got the chord PT here. You can use either one. And essentially what I'm saying is from those points on your circumference P and T, we can follow the lines, we can follow the radii up to the point where they meet at the center. But from those same 2 points, we can also follow the 2 chords, PR and TR, to an angle at the circumference. And so what we have is an angle created from the same chord or from the same arc to the center, and an angle created at the circumference. And that's how I know that that POT is equal to double PRT.
Okay, ma'am. Thank you, ma'am. So as long as
Pleasure.
the two, if you can see like maybe, for example, PT, which is like I would say the common side, then you could just make that conclusion whereby angle O would be 2 times angle R2. Basically.
Exactly, because they both have a common chord from which they originate.
Okay, ma'am. Thank you, ma'am.
Good. Any ideas on getting R1, guys? I saw a hand and then the hand disappeared. Any ideas? Rato?
So, ma'am, what I think we would do, since angle R in total is at the circumference, it would be a 90-degree angle. So we could say 90 minus 42 degrees, and then we can get R1.
Why are you saying it's a right angle?
So, ma'am, since in the description they tell us it's a cyclic quad, and also it's an angle at the circumference, which angle at the circumference is a 90-degree angle, and also with the cyclic quad, basically, I think I forgot the word, but then two angles make 180 of a cyclic quad. So it would be that the R, which would be a 90, it would be basically 180 divided by 2, because even angle, I think that's a Q, I can't see properly, but it'll also be a 90-degree angle. Basically,
Okay, so we just need to be careful. We can only assume, or we can only say rather, that an angle is 90 degrees on your circumference when it is subtended by a diameter. So only if this line is the diameter can we say that this angle is 90 degrees. We don't have a diameter here. So unfortunately, we can't then assume any angle is 90. For the cyclic quad situation, I do agree with you that, and the one you were trying to describe here is opposite angles of a cyclic quad. But this is a cyclic quad. The angles very clearly aren't 90 degrees. What it does say to me, though, is that opposite angles of my cyclic quad are supplementary. So when I add them together, they must give me 180, but they don't necessarily have to be 90 degrees. It could be 180 or 30 and 150. Okay, so just be very, very careful. We need to have a diameter in order to say our angle is 90 degrees. So, cool. So we've got an answer on the chat, which is awesome. Teko, do you want to explain it, or would you like me to explain it?
I can explain it. I don't mind.
Awesome.
So basically, by the angle T, I used angles on a straight line to get the angle of T.
Okay, so this angle over here.
Yes, right there.
Perfect.
And then I know that R1 is equal to angle T because they tell us that QR and QT is equal, so the opposite angles are equal.
Perfect, exactly. So angles on a straight line, to get this angle QTR, which gives us 34. So 180 minus 146 gives us 34. Straight line. And then exactly, because we were told that QR is equal to QT, the angles opposite those equal sides are equal. So angle R1 is also equal to 34 because of angles up equal sides. Okay, so look out for, again, information that we've given you. If you think about the information that we were given and what we've used the fact that we know where the center of your circle is, and we've used supposed radii to some extent. We have now used the fact that QR is equal to QT and the fact technically that we had a straight line in RTS, and we were able to find angle R1. Okay. Obviously, the problem with diagrams and drawing all over the place is that it does become quite chaotic, but we will survive. So now I know that this is 34 degrees and this is also 34 degrees if potentially that's useful to me at some point. But the third angle that I'm being asked to find here is the angle RPT. And RPT is this entire angle down at the bottom here. So again, I'll give you a second to think about it. RPT. And Russell, this is potentially where that opposite angles of a cyclic quadrism could come in. If you have any ideas, just let me know. Otherwise, I will give you a second to have a look. I know that sometimes you do just need a second to have a look. Nice, Leila. Do you want to explain it? Lorato, nice. Tejo, nice. Tukazani, nice. Oh, we all just came in. Sorry. I don't know why I didn't see all of them. So, Tukazani, I see you got it correct. Do you want to tell us? You don't have to. It's absolutely fine. Leila, do you want to explain it? So obviously, as I'm asking all of you to explain it, I get kicked out, which is cool. So,
No, ma'am, it's okay. I'll explain it.
okay, Leila, I'm ready.
Okay, ma'am, I use the sum of angles in triangles of a triangle in TRO, I think. So 34 and 34, I just said 180 minus 34 minus 34, and I got 112. And then I just said the opposite angles of a cyclic quad are supplementary. So then I said 180 minus 112, and then I got 68.
Lovely. RPT. Perfect. Okay, am I still working for everyone? I know I had a bit of a moment there. Okay, I'm going to assume you can all hear me and see me, and we're there. Okay, so exactly as Leila's just explained. Perfection. Okay, great. There's our triangle, beautiful triangle. We can work out this angle at Q, and then we know that Q plus whatever this opposite angle is must be equal to 180 because of our opposite angles of the cyclic quad theorem. And so exactly once we know this is 112 degrees, we can just subtract it from 180 and get 68. Okay, so far, except for the cyclic quad and the angle at center, all of our other reasons have been reasons that we've been using since grade 8. So this is why I said to you, you've been doing this for years now. And even though we think, oh, it's circle geometry, I don't use the stuff that I've learned previously, you do. Okay, so we have to still remember the basics when it's Euclidean geometry. Okay, so this is just an example of that first question that you're going to get, a relatively easy, straightforward Euclidean geometry question that eases you into it. There won't be any algebra, so there'll be no variables. It'll all be numerical, and then it leads you into an algebraic example. So I'm just going to wait here for you to screenshot, and then we'll have a look at that next type of example. And obviously, guys, you know, if you've got questions, you just let me know as we go along. Okay. Right, so this is now where things, I feel like they kind of lead you into it, and then they're all of a sudden like, haha, swim, panic. So if we look at this diagram, I also initially looked at it and I was like, there's so much going on, but we need to break it up. So let's ignore the diagram for a second and let's just read the information. So it says in the diagram, two circles touch internally at M. MK is a common tangent to the circles. AE and C are points on the larger circle, and B and D are points on the smaller circle. Chord CA is produced to meet the tangent at K. Triangle MEC is drawn. CA and EM meet at B. K is a tangent to the smaller circle at B. D is a point on CM, and BD are drawn. K and B equal X. Now, a lot of this information I don't want to say is pointless, because it isn't. The reason we give you information such as D is a point on CM, so that there is no confusion about where that point sits. We already told you D was a point on the smaller circle, so you know it's a point on the circumference, but it also happens to be a point on this line. The reasons we say things like chord CA is produced to meet the tangent at K is that you understand that this is a continuation of the same line. So CBAK, this is all one straight line. So it's not that those bits of information aren't important, but there are sort of pieces of information that just make it explicit what is happening in our diagram. Right, so we're going to do a Dr. CPT, and we're just going to identify the things that we have. So I was told that we have some tangents, so that's quite useful for us. So MK is a common tangent, and we were told that there's a tangent, that KB is a tangent to my smaller circle. If you want to do them in different colors, you can do what you want, but let's highlight our tangents. So here's MK. And KB. Now immediately, just by highlighting that, immediately I can see that I've got tangents from a common point. And so I can start thinking about what that might mean for me. Right, but they're my tangents. We're told that AEC are points on the larger circle, so they sit on the circumference, which means that if I had to join them potentially with point M, I have a cyclic quad. Chord CA is produced to meet the tangent at K. We've already spoken about that. Triangle MEC is drawn, so we can see that triangle over here. It's not really something you need to highlight, but you can see the triangle MEC if you want to see it. It's there. So now I've done that. CA and EM meet at B. So there's B, CA, and EM intersect at that point. Just really making clear for us it's a point of intersection. And as we've already spoken about, we've got D on MC, and we've got the line segment or the chord AM and BD drawn. Okay, so we have some tangents. We potentially have some cyclic quads. We would just have to join the points. So we can kind of imagine them for now if we want. We don't have any radii. We don't know where the center of our circles are, so I don't have radii, diameter, nothing like that. I don't have any parallel lines. And like I say, in terms of the cyclic quad, we potentially have them, but we can't necessarily see them without imagining a chord that exists. All right, but this is all of our information. We're going to have a look and see what we need to do. So, I don't know why I've made a choice to put that so far away. Just make our lives easier here for a second. I'm going to make it bigger again, don't you stress. More so that we can see what we're doing. So the first question says, name, giving reasons, 4 other angles each equal to x. Okay, so importantly, we were told in the information that KMB is equal to x, and we can see that there. So KMB is this entire angle, essentially M1 plus M2. So we need to find 4 other angles equal to x. Now again, think about what information you were given. You were given tangents, you were given the triangle information, but the tangents is probably a fairly good one to start off with. And the reason I'm saying that is because, as I said to you earlier, one of your tangent theorems is that when you have tangents to a circle originating from a common point, okay, so here's my common point. The distance between where it touches the circle and the common point on both tangents is equal. So here's my common point K. Here's my tangents to my smaller circle KA, KB, and KM, which means that these purple lines that I've drawn in here are equal to each other. And if those 2 lines are equal to each other, that means that the angles opposite them are equal. So this whole angle B1 is equal to x. And immediately now that I know this is x, I would fill it in for myself. Because as I start to fill it in, hopefully I'm going to start to be able to see what other angles are also equal to x. Right, so I've given you one that's equal to x. Hopefully that's going to help you with a few others. I want you to have a look. Again, think about what information you've been given. Think about where your tangents lie and all of that fun stuff. And then let me know which other angle you think, or which other angles you think are equal to x. We need another 3 still. And obviously with a reason. Marato?
Ma'am, I just have a question. So the tangent, which is by K, where the common point is K, it ends by B and M. It doesn't like extend all the way, like maybe the side with where there's angle B, it doesn't extend all the way to C. It ends just by B.
I mean, I suppose technically it does. Sorry, I didn't just really think to highlight that. It does extend all the way. That's still part of the same tangential line.
Okay, ma'am. So it wouldn't be wrong for us maybe to, when we're proving for B1 to equal to X, instead of including the entire tangent, we just like end just by B1, technically.
I mean, you could, yeah.
Okay.
So the thing I'm saying in terms of the tangent from a common point situation is that it is measured, or we measure the length from the point of intersection with your circle to the common point. So this is the length that is equal on the other side. We wouldn't include BC, but BC is still part of the tangent. Sorry, guys. I don't know what is happening. I don't know where I lost you, where we're at. Rato, I know I was explaining something. Let me know if you got all of it. If you didn't, I will do it again.
Ma'am, I didn't get everything because you froze. So if you don't mind re-explaining.
Absolutely. This is my life at the moment. Okay, so let's go again. So what I'm saying in terms of the tangents from a common point is that when we measure from the common point to where the tangent touches the circle, this is the segment that is then equal on the other side. This tangent continues for BC, but that doesn't, or that's not part of the length that we're saying is equal. We're only talking about from point of contact to point of intersection, essentially. The tangent can extend. So here in this diagram I drew up here, this tangent could extend, but it is only this section between points of contact that the tangents are then equal for those segments.
Okay, ma'am. And then I wanted to ask, when we're stating our reasons, we don't necessarily, do we have to say BK is equal to KM, like the sides, when we're saying angles opposite equal sides?
We should.
Okay.
So yes, technically I should have done that. As I was talking about it earlier, I was like, oh, should have said that. As far as I remember, the mark allocation was actually only for saying B1 equals X and then angles of equal sides. But yes, technically we should say KB equals KM, tangents from common point. Okay. Right, so I was asking something. Oh, what other angles for X do we have? Does anyone have any suggestions? Okay. I know this has been chaotic, so I'm just going to go. You can jump in if you feel you have something. First thing I see is now that I filled in that B1 is equal to X, I can see that these two angles are vertically opposite to each other. B4 and B1 are vertically opposite. So angle B4 is also equal to X, vert up angles. Okay. And now this is where your tangents come back into play. We need to think of our tan chord theorem. Now, I'm going to be honest, I sometimes struggle with tan chord theorem to see it, but there we go. Lovely. Okay, so C2. Hang on. So just be careful. So C2 is over here, which means that we would be looking at just this angle in terms of tan chord theorem. So you're on the right track with tan chord theorem, absolutely. But just be very, very careful with the tangents and the chords you're working with. So following your train of thought, if we go into almost the same triangle, but the triangle MEC, here's our tangent, here's our angle X, and so the angle equal to X according to my tan chord theorem is this whole angle C. So ECD is equal to X. Tan chord theorem. And guys, this is such a silly thing. Please make sure you do actually write theorem. You'll lose a mark if you don't. You could just say THM, that's fine, but make sure the theorem bit is there. Renton D1, I'm pretty sure I got that as well. Lovely, okay, and D1, same reasoning, tan chord theorem, but now here's my tangent. We're now in the smaller triangle. There's my angle X, and so D1 is equal to X as well. I'll take all the colors off now in a second because I know it's a lot. But because we had two tangents to the bigger circle and the smaller circle, we can use it in both. So nice, Brenton, well done. Okay, let's just take off these scribbles and then we will put in what we need to put in. There's way too much happening here. So this is why I'm saying what I said earlier, guys. You can use colors if you want, but I'm also fully aware of the fact that it can be overwhelming. For me, I like to use colors. It's helpful for me and the way my brain works, but if it's not helpful for you, don't use it. Okay, there's absolutely no reason why you should use something that doesn't work for you. Okay, Kirsten, I did see your question. I'm going to get to you now. I'm just going to fill in all of our X's that we have, just in case that's helpful for us. So B1's X, D1's X, this entire angle here is X, and this angle is X. So we've got our 4 angles that are equal to X. Okay, so Kirsten, you'll have to put it on the Google Classroom and I will attend to it at the end of the lesson, okay? So you can just post it on there. On the homepage, I suppose you would call it. You can make a post and you can just put it as a picture there and then I can have a look. Okay, so now we've got all of our X's. And this should now help me as I move into the next question. So 9.2 is saying prove giving reasons that BD is parallel to EC. So firstly, when we are trying to prove something, if it is parallel lines, we would either need to prove that corresponding angles are equal or that co-interior angles are supplementary or that alternate angles are equal. That's how we prove parallel lines. You could use proportion theorem. So if you could show that line segments of your sides are in proportion, you could show that lines are parallel that way. But obviously we have no lengths here, so we're not able to show any sort of proportion because we don't have that information. And then in terms of proving cyclic quads or proving that a line is a tangent, then it would be all of your converse reasons. So converse tan chord theorem, converse angles and same seg. Our converses are generally used to prove cyclic quads and tangents. Okay, Kirsten, yeah, that's fine at the end of the lesson. All right, so we are wanting to prove BD is parallel to EC. Now, immediately, like for me, this is how my brain works with geometry. Just by highlighting those 2 lines, I can immediately see that they're parallel. The reason I can see that is because D1 and this angle C are both equal to X. And if you have a look, there's your F shape. So these are corresponding angles. I have already proven that the 2 corresponding angles here are equal. And so I can say that my lines are parallel. Again, 2 marks, so it shouldn't necessarily be a huge amount of working out. So we know that angle ECD is equal to X. We know because we've proven it. Remember, if you've proven something already, you don't have to reprove it. We also know that D1 is equal to X. And so they are then equal to each other because they're both equal to X. And if ECD is equal to D1, that means that BD is parallel to EC because corresponding angles are equal. Now remember, in your proving of parallel lines, you're not going to say corresponding angles EC parallel to BD like we usually would if we were using the parallel line reasons, because you're proving that they're parallel. So the fact that they're equal means that they are parallel. Versus if I told you they were parallel, you could then tell me the angles are equal. So we're doing the opposite, the converse. So by showing that they're equal to each other, we have proven that those lines are parallel. Okay, Leila?
Ma'am, I wanted to ask, if you say, for example, in 9.2.1, you don't manage to prove that, like, for some reason, you don't manage to prove that BD is parallel to EC, for any other question where they, like, require for you to use BD is parallel to EC, would you just assume that they're parallel?
You could, yeah, because if I'm asking you to prove it, then it's provable. So yeah, you could. Cool. Tukozani? Togozani, you there? Oh, okay. We'll come back. Lorato?
Ma'am, I have a question with how you stated it. So would it also be fine if you said angle ECD is equal to D1, which is equal to X, and then we can just say proven instead of separate them, and then we can just immediately go to their parallel because of corresponding angles. Okay.
Yeah, so that's how I initially did it. I was more just writing it out so that we knew what was happening.
Okay,
So guys,
ma'am.
if you can sort of put it all together, that's absolutely fine. So what Lorato's saying is, why did I do all of this when I could just say ECD is equal to D1 is equal to X, because I've proven that they're both equal to X. That's fine. And then you go straight to your conclusion. Yeah, it's more for purposes of our learning, but that's absolutely fine. No problem whatsoever. Okay. TikTok is on it back, so we'll just have to come back to that. All right. So we've got that. We now know that they're parallel. And like Layla said, if you couldn't prove that they're parallel, you can now sort of assume that they are in case it helps you in your next question. So the next question is asking me to prove that angle A2 is equal to B2. Who knows why I've got arrows, but whatever. So here's A2. Here is B2. I want to prove that those two are equal to each other. Now, this is worth 3 marks, which likely means that I'm going to have to do a little bit of working out. Okay. Now, what I want you to remember is that I'm going to give you a little hint, and then I'm going to let you think about it. At the start or in the information of my question, it said to me, and let's just do this. It said A, E, and C are points on the larger circle. And it said the two circles touch internally. There were so many words that are combined into one there, at M. So what that means to me is in the big circle, M, A, E, and C are all on the circumference. And this is what I was saying earlier. We do have a cyclic quad. So if I were to go and join or draw a chord AE, EAMC is a cyclic quad because all 4 vertices sit on my circumference. So I'm going to give you a second to think about this. The cyclic quad thing, I'm pointing it out, so it's obviously useful in this question. Have a think. I'll give you a minute or 2, and then we'll have a look at showing that angle A is equal to A2 is equal to B2. We're going to do that. But have a think. Like I said, the cyclic quad thing, important, useful. Any ideas? Tejo?
Ma'am, I think we use similarities to get A2 and B2 to be the third angle, because I used triangle MEC and triangle MBD. So I got the angle ET equal to A2, and then I said we found that angle C is equal to D, which is already proven, and then angle M is the common angle, and therefore B2 will equal to A2.
Can you say the first bit again? Sorry for me. Which angle did you say E is equal to?
E is equal to A2 because of angles in the same segment.
Okay, so I like where you're going there. How does that link with your similar triangles though? Because you're saying that you're working in the triangle MEC and MBD. So angle A isn't in those triangles.
Yes, but angle E is equal to A2. It's the same value. So
Oh, sorry. Okay, I'm on the same page now. Right.
Okay.
I'm there. Okay.
Yeah.
Sorry, I'm there. So, yeah, perfect. You don't actually even need to go prove similarity. So you'll see why in a second. Because once you made that first statement, so once you said that, so guys, if we're not following, in the cyclic quad that I have, here are your angles in the same seg. It's like a bow tie situation. So A2 is in the same segment as angle CEB. So CEB is equal to A2. Angles in same seg. The reason I'm saying we don't even need to use similarity is because you have already proven that EC is parallel to BD. This angle CEB and B2, they are corresponding angles because of those parallel lines. If you didn't have the parallel lines, then yes, you would have to prove similarity, but we do have the parallel lines. So we can say angle CEB is equal to B2 corresponding angles. And this goes back to, again, what Layla said. You could assume that the lines are parallel even if you couldn't prove it. BD parallel to EC. And because A2 and B2 are both equal to the same angle, they have to be equal. And if you wanted to put a reason, you could say both equals CEB, or you could put that over here. But because they both equal the same thing, they are equal. Like I said, you could use similarity. I mean, you'd get 4 marks or the similarity method. You just don't need to because you did have the parallel lines. But that's awesome. Did not even think of similarity. So awesome, awesome. Well done. Okay, 9.3 is asking us to prove that ME times MD is equal to MC times MB. Anytime you see something like this, you automatically need to think of proportion theorem, okay? Anytime I'm giving you something like this, probably going to be a bit of a proportion situation going on. This is, I don't know where I was going with that statement, so you can just ignore me. Sometimes things come out of my mouth that I haven't thought all the way through. Okay, so let's first identify where those sides are. The reason that we want to identify where those sides are is so that if we do need to use some sort of proportion, we know sort of what triangles we're working in. So ME is this side length over here. MD, this side length over here. MC, the whole side length. And MB, a portion. So what we can see is that we're kind of contained to that triangle MEC. We're not sort of going in weird and wonderful places. I'm in this triangle MEC. So just so that we can work with the diagram, I'm going to do this question's answer up here. 9.2.3. So like I say, this triangle clearly quite important. And they highlighted it, or they pointed out that we were given this triangle, that this triangle was drawn for us in the information of the question. So again, clearly somewhat important. Now in this triangle, obviously we know a few things. We know the corresponding angles are equal. Essentially, we actually know that they're similar because we have all 3 of the angles matching up with each other, and we know obviously our parallel lines. Because we've got those parallel lines, so if I were to just take this piece of information out for us, MEC, ED, parallel. This little diagram of just the triangle with those parallel lines should immediately be screaming proportion theorem to you. So what we can now do is we can set up our ratios according to our proportion theorem, because that's essentially what we have. We've got the line parallel. So we know that, and obviously you could set up several different ratios, but we obviously want to set up the ratio that works with these sides. So we know that ME, remember the whole long side here, to MB, the smallest segment at the top, is in proportion to the whole side length, MC, to the little segment at the top, MD. And this is all because of my prop theorem. Because I was given that parallel line, or I've proven those lines parallel rather, I know I can use my prop theorem. EC parallel to BD. Okay, now once you've got your ratio, it is quite literally a case of manipulation. Whenever you get these sorts of product questions, sometimes there's like a squared in it or anything like that is manipulation. Now, if we have a look, we want the ME and the MD to be together. We also then want MC and MB to be together. Now, if you have a look at where they are, they're at cross multiples with each other. So quite literally all I'm going to do is I'm going to cross multiply this ratio and I'm going to get what I want. So if I multiply both sides by MD, I get ME times MD. If I multiply both sides by MB, I get MC times MB. That's exactly what I wanted. I have to do nothing more. And again, if you look at it, it's worth 2 marks. We're not supposed to be doing wild and wonderful things. We're using proportion because of those parallel lines. So remember, when you have a line parallel to one side of your triangle, it divides the other 2 sides in proportion. That's what the proportion theorem states. If we've forgotten the proportion theorem, because honestly, it's not one I particularly enjoy in any case. There it is. A line parallel to one side of a triangle will divide the other 2 sides proportionally. We have that. We have the line parallel to one side of our triangle. So we could use that in answering this question. So like I say, whenever you see weird things like this, I don't know if we'll get to this one, so I'm going to just show it to you. Or something like this 10.2.4, where there's products and they're equal to something, proportion. Okay, always, always proportion. All right, so I'm going to do that. Let's take a screenshot. Like I said, I don't think we'll get through all of question 10, but we'll see how far we go. And we will carry on. We will move. Okay. So like I say, guys, nice numerical example to start off with. Then it gets into the algebraic stuff. The next question is 10.2, so I'm fairly certain it's in a theorem proof, and then moving into slightly more complex examples. Okay, so let's have a look. Sorry, there's a lot of space now since I moved my questions, but it doesn't matter. So in the diagram, AB is a diameter of the circle centered at O. Sorry. Triangle ABS is drawn with S a point on the circle, M is a point on BS, and OM is produced to T such that AS is parallel to OM. TS is drawn such that BOST is a cyclic quad. So we've been given a fair amount of information here once again that we are hopefully going to be able to use to answer some questions. So again, it's just Dr. CPT it. This time I am told where the diameter is, so that's quite useful. Like I said earlier, if you know where the diameter is, and if this diameter subtends an angle on your circumference, which it does, we know that that's 90 degrees. So I'm actually just going to fill that in immediately because I know that. We've been given, what was a triangle ABS? We can see that there. S is on the circumference. That's potentially an important piece of information for us to know. We're given parallel lines, so we're told that AS is parallel to OM. And it does tell us that OM is produced to T, so that's what I was saying earlier. It means it's all one straight line. The next bit of information we're told is that BOST is a cyclic quad. BOST, not the greatest quadrilateral I've ever drawn in my life, is a cyclic quad. Now, what that essentially means, grade 12s, is that even though there's no circle there, we can imagine a circle passing through all four of those coordinates. And so we have our cyclic quad. So essentially all it's telling me is that I could draw a circle between those or through those 4 points, and they will lie on the circumference of my circle. So the first question says, prove giving reasons that TS is a tangent to the circle at S. So here's TS. I want to prove that at this point S, that line TS is a tangent to my circle. Now, proving tangents is two ways to do this. Way number one is to prove that from your center, the line drawn to the point of contact with your tangent meets at a right angle. Remember, tan per Brad. The second way to prove that a line is a tangent is through your tan chord theorem. So, oh gosh, sorry. If you can prove your angles are equal according to tan chord theorem, obviously converse, you've proven that a line is a tangent to your circle. Now, in deciding which of these methods to use, look very carefully at what information you have. So what I mean by that is we don't have a radius drawn. Obviously, we've got OB and OA, and that's fine, but OB and OA have no connection to that point S, that point of contact. So that's a little bit tricky for me. Obviously, I've got the line OS as part of my cyclic quad, but that wasn't drawn in. So try and avoid stuff that you are having to join in, to construct in your diagram. And so that kind of really only leaves me with my tan chord theorem. It kind of only leaves me with trying to prove that the tan chord theorem exists here, that my angles are equal. All right, so we need to just be very careful when we have a look at these things. But let's go back to the information we're given and try and use what we have. So we've got some parallel lines that could give me some corresponding angles, some alternate angles, co-interior angles, all of that fun stuff. And we were given the cyclic quad. So if we go to the parallel lines first, for example, O1 is equal to angle A. Those are corresponding angles. Same as M1 would be equal to S1, corresponding angles. If we go to the cyclic quad situation, angle O1 is equal to angle S2 because of angles in the same seg, and immediately we should see that's exactly what we want to do. But we also have other angles in the same seg. Let's maybe not use another circle. Let's say angle OBM is equal to angle T. Right, now if I have a look at what I've drawn here, and this is honestly sometimes, guys, just how you have to do it. You start filling in things until you can see what you want. What we should see is that in proving that O1 corresponds to A and that O1 is equal to S2, I'm essentially proving that S2 is equal to angle A. I am showing that the tan chord theorem is in play here. And so that is how I can prove that this line TS is a tangent to my circle. I'm just going to move that here so we can do this working out here. Now again, it's not necessarily always the easiest thing to see, and I understand that. And that's why I'm saying sometimes it helps to just start putting information onto your diagram that you know is true. Once you start doing that, you start to see what you have to work with in order to get to where you need to be. So let's write down what we said. You could start anywhere, but I'm going to start with my corresponding angles. Angle O1, we said, was equal to angle A. Now remember, we can use angle A. You could call it BAS if you wanted to, but it's the only angle we have here at point A, so it's okay to just say A. We say that's equal because of corresponding angles. TO is parallel to AS. Obviously, if you said OM is parallel to AS, absolutely fine. We also knew that O1 was equal to angle S2 because of angles in same seg, because we were given that cyclic quad. Again, what we give you, the information we give you for a reason. We want you to use it. So I've used the parallel lines. I've used the cyclic quad situation. I'm using the information that was given to me. And so because angle A is equal to angle S2, because they both equal angle O1 essentially, we can say that TS is a tangent. And our reason is converse tan chord theorem. So like I said earlier, converse reasons are used to prove that something is a tangent, something is a cyclic quad, parallel lines, etc. Converse tan chord theorem. We use the word converse in the tangent theorems and in the cyclic quad theorems. The parallel lines, as we saw earlier, we don't use converse, but we say that the angles are then equal, or that in the case of cointerior, they are supplementary. Now again, it almost goes back to what Layla said earlier. If you couldn't prove this, move on to the next question and assume that TS is a tangent. It might then help you in answering the next thing. But again, grade 12s, if you struggle, just start filling in information. As long as you understand why you filled in the information, you could put a reason to it. Fill in information and see how having that information potentially helps you get to where you need to be. Okay, so now we know TS is a tangent, and maybe that's going to help us later on. Right. The next thing it's asked me to prove is that TS is the diameter of a circle passing through the points T, M, and S. So now we almost need to imagine a whole nother circle situation going on here. So T, M, and S, essentially a circle that looks better than that, but going through those points. Prove that it is a diameter. Now, what I want you to think about is we only know a line is a diameter if we can show that the angle it subtends on the circumference is 90 degrees. We already know, because we said right at the start, because AB is the diameter, that's highlighted in blue, and it told us in the information of our question, AB is a diameter. We already know that S1 is equal to 90 degrees. That's information we know. We also know, because we spoke about it now, that M1 is also equal to 90 degrees because it is a corresponding angle with S1. And look at that, I've proven it. M3 is vertically opposite to M1. There's the diameter because it subtends an angle of 90 degrees on the circumference of that circle. So again, just by filling in information that I have, I could get to where I needed to be. Okay, now that's 5 marks. And granted, yes, I understand that I have done this for many years and we got there quite quickly. But all of this information I already had. Because we did the initial analysis of my question, understood what AB being a diameter meant, understood what the parallel lines meant, understanding all of the things I can apply, that was quick and easy. I knew the corresponding angles because I'd identified my parallel lines. I knew that S1 was 90 because I'd identified my diameter. Vertically opposite is something we've been using for 5 years. Okay, so 5 marks should not scare us. It's not necessarily going to be a huge amount of work. Remember, reason marks get included. But just remember, the analysis, that initial analysis of your question is so useful. Okay, so the first thing that we know is that S1 is equal to 90 because AB is the diameter, so angles in semicircle. The next thing that we know is that because of corresponding angles, M1 is also equal to 90. And we have got OM parallel to AS. And because M1 is equal to 90, we know that M3 is also equal to 90 because of vert-op angles. And because that M3 is equal to 90, we can say that TS is a diameter. Because of converse angles in, it's not how you spell converse, is it? Angles in semicircle. Okay, so 5 marks seems like a lot, but it's your marks, your statements and your reasons. So converse obviously gets a reason. You'd probably get 1 mark for the vert-op situation, and then statement, reason. Generally, if you're not sure, if it's like a grade 8, grade 9 level reason that you're using, that'll be 1 mark for both the statement and the reason. That's a lot of marks that I've just put there, sorry. Can't see my ticks now, it's not 5, there we go. Grade 10, grade 11, grade 12 reasons with circles and prop theorem and all of that, generally it's a mark for the statement and then a separate mark for the reason. Okay, but again, our initial analysis of our question allowed us to answer this easily because I had all the information there for me. And even if it means grade 12s that before you even start answering questions, you're filling in information like the 90 degrees, the corresponding angles, the angles in the same seg, so that you have it. Ooh, excuse me, do it. You're doing it in pencil anyways, it doesn't matter. And also remember, we can mark stuff on your diagram. So let's say, for example, you had done your initial analysis of your question, and in that analysis of your question, because it said AB is a diameter, you had gone and said that's a 90-degree angle, and you had gone and said that's a 90-degree angle, and so therefore that's a 90-degree angle. I can mark that stuff on your diagram. Yes, you're going to lose the reason marks, and you're definitely not going to get 5 full marks, but I can mark what's on your diagram. At the end of the year, we will mark what is on your diagram. So always just remember that filling stuff in on your diagram, particularly, there was too many lilies, particularly in a question where you're not 100% sure of what to do, put it on the diagram. You can get some marks there. Yes, we're going to lose our reason marks and final answer marks, and that's not the end of the world, but at least you can get something. So always just remember what is on your diagram we can mark, and so fill stuff in, particularly in that pre-analysis stage of your question. Okay. So I'm going to just stop here for you to take a screenshot. Right, the next proof that they want us to do is similar triangle. Obviously, I jinxed myself by saying, oh, we've got time, we can do this. She was wrong in so many ways. Okay, so now we've got 2 minutes, and we will not be able to do this in 2 minutes. So I'm going to leave that there for you. We can do the similar proof on our Wednesday. And hopefully whatever issues my internet is having will have dealt with before then. So I'm going to just stop here. You can take a screenshot. You can do the proof of similarity. Yeah. For Wednesday, and we will have a look at it on Wednesday, and we will carry on with our Euclidean geometry. If you would like to leave the chaos that has been this past 90 minutes with me, thank you for staying. It was a real joy, and I appreciate you. And we will see you on Wednesday. Best of luck with the rest of your exams. And I will see you on Wednesday. Fully aware of the fact that Kirsten, you wanted to ask a question, and Lorato, I see your hand. So I'm going to deal with that. Lorato, let's start there.
Ma'am, so I have a question with the topic itself. So my first question is, when it comes to the proving, will we ever get a question that they tell us, maybe, for example, with the parallel lines? Would they ever tell us to prove parallel lines that are not exactly parallel?
So when you say not exactly parallel, do you mean they don't look parallel?
Like, ma'am, they will tell you, maybe the question just says, prove BA is parallel to DC, but then when you work it out, you can see that they're not parallel. Will we ever get a question like that, or will it always be they are parallel? You just need to show what makes them parallel.
Yeah, it usually the latter. I have never seen a question asked where it says prove that this is true, but then it actually ends up not being true. Usually if I'm telling you TS is a tangent, it's a tangent. You need to prove it, but then like we said earlier, you could then assume in later questions that it is.
Okay, ma'am. Then I wanted to ask, so would we ever get basically it's a circle, like a big circle, and then there's a tiny circle like right in the middle, and then there will be a cyclic quad from the circumference of the small circle, like maybe a side of a cyclic quad from the small circle circumference all the way to the big circle circumference, and then they just join each other to make like a whole cyclic quad. Will we ever maybe get a question like that?
A cyclic quad like that?
No, ma'am. Maybe like it extends to the other side. The bottom side also extends to, yes, something like that.
Like that?
Yes, ma'am. Will that also be classified as a cyclic quad? Or
so I'm going to say no, but let's just take off that. So that is not a cyclic quad because it doesn't, in terms of the vertices we have, vertex, 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 that bad boy is not on the circumference, so it's not a cyclic quad. These three are not on the circumference of the smaller circle, so not a cyclic quad. But we could, almost like what we had in this question, what often happens is that you've got common tangents. So this was a tangent to the smaller circle, and this was a tangent to both the bigger circle and the smaller circle. So common tangents is a little bit more likely. That's the word I'm looking for.
Okay. So, ma'am, if we were to ever stumble across something like this, would we maybe let's say they say, is ABCD a cyclic quad? Then would such a question maybe be 2 marks? Because it would you just need to explain the fact that one of the vertices is not exactly.
So yeah, if it was like a 2 marker, yes, but just remember you could potentially prove that there is a whole nother circle that all 4 of them go through. So just be careful, but yes, if it was just like a 1 marker, 2 marker, or give a reason why it's not a cyclic quad, then you would just say because not all 4 vertices are on the circumference.
Okay, thank you, ma'am.
Okay, pleasure. Okay, Kirsten?
Hi, ma'am. I have a question. So this was in today's paper. We wrote Maths paper 2 today.
Mm-hmm.
And we were given like a circle, and we were given the equation of the circle. So I was able to determine the center, and we were given from the equation we can tell like the radius, obviously, because it's radius squared in the equation. So then they asked us to determine the equation of the line, that like the diameter that's running through the circle. So would you then use the distance formula in reverse to be able to like get the other coordinates? But I was trying so many different ways, but I don't know how to eventually get to that.
So was the only information you had the equation of your circle and the radius?
Yes.
And they wanted the equation of the diameter?
Yes.
Assuming that the diameter was the extension of this. Okay. I assume the diameter was drawn in for you.
Yeah.
Okay. Okay. So you only know one coordinate, which is obviously problematic. You didn't know anything about where it touched the circumference.
No, like not at all. That's why I was so confused, because they didn't give us like another coordinate. So I was trying to like maybe find, is there any way to find another coordinate if you have the radius and if you have the center?
So that's the problem. I mean, like the thing is, because obviously this radius could be anywhere, right? I could draw this radius anywhere.
Yeah.
So, and this would be the midpoint of your diameter. I'm sorry, I'm now scribbling because this is how my brain works. Do you remember how many marks it was out of?
It was a 5-mark question.
Oh, my Lord. Okay. Okay.
And this was like the only information that they gave us in the circle, and everyone was so confused about what we should do.
Do you remember what your center was?
I think it was, I really can't remember. We wrote this.
Don't worry. No, don't worry. Okay. So we have that information. We know X and Y, and we know that. See, because I'm only thinking like if you had maybe like if you knew like a tangential line to your circle, then that would be useful, because if we had our circle and we know,
able to use like the tan perpendicular to radius. Yeah.
And we could also then, so like if, for example, your center was at, I don't know, 5, 3, it means that where it then is touching your y-axis, that's at 3. So you have then another coordinate you could use.
Yeah.